We've seen that the first derivative can tell you when a function's increasing or decreasing. And so the first derivative says a lot about what happens to a graph. For example, here, I know that the first derivative is positive up until this point, negative until I get to this point in my x values, and then after that it remains positive. We also saw from the first derivative test that since the first derivative goes from positive to negative here, I have a local max, and since it goes from negative to positive here, I have a local min. But what about the second derivative? What does the second derivative tell you about the function? I understand that the first derivative gives me the slope or the instantaneous rate of change at any given moment on this graph, but what about the second derivative? The second derivative would say the instantaneous rate of change of the instantaneous rate of change. What does that look like physically? Well, that would be the instantaneous rate of change of the slope. So in other words, yes, my slope is increasing up into this point. It is increasing up to that point, but it's not getting steeper as I go. As I get closer to this maximum, the slopes of these tangent lines are actually starting to decrease. And so the slope of the tangent lines are decreasing. That means that trend is decreasing. That would come from the second derivative. It would tell you the instantaneous rate of change of your instantaneous rate of change. All that to say that the second derivative tells me my concavity, and the concavity is the way you bend. Are you bending up or are you bending down? Okay, are you opening downward or are you opening upward? So for example here, I can see that up until about right here, up until about right that point, this thing is bending down, and we call this concave down. And over here, I'm bending up like a bowl. This is called concave up. Okay, so concave down are your hills, and concave up are your bowls, or your valleys if you want. Okay, now so the second derivative says something about the concavity. What does it say about the concavity? It says this, that when you're concave down, that means your second derivative, or the trend of your slopes of tangent lines, is decreasing, so your second derivative is negative. And on the other side, your second derivative is positive. Okay, so how did you determine that? You determine it the same way you determine increase or decrease. Instead of using the first derivative, though, you use the second derivative. And this point in the middle, where it changes, that's what we call an inflection point. And how do you find inflection points? You set the second derivative, so I'll say second derivative of c equals 0, where c is an inflection point. Another place you might want to test to see if your concavity changes is when the second derivative is undefined, which is not here, but if you have an asymptote or something like that, you can have a change in concavity. So here we should say also check when your f double prime is not defined. Okay, let me show you an example of how this works. Okay, here I want to determine concavity of f of x, which is 4x cubed plus 3x squared minus 6x plus 1, and I also want to find inflection points. Okay, so we just saw the concavity comes from the second derivative, so I need to find the second derivative, and so in order to do that I need to first find the first derivative. Okay, so the first derivative here is 12x squared plus 6x minus 6. Okay, that's not too bad. And then so the second derivative, since this is a polynomial, these are pretty easy. My second derivative here is 24x plus 6. Okay, so first I need to find when is this thing equal to 0, and that is how you find your inflection point, which is actually something they wanted us to determine. So the inflection point comes from setting this 24x plus 6 equal to 0. So this is pretty simple algebra here. We end up with 24x equals negative 6, or x equals negative 6 over 24, which would be what? Negative 1/4. So your inflection point occurs at negative 1/4, and so your inflection point is actually negative 1/4 f of negative 1/4. And if you're careful in the arithmetic, you should get that that is actually negative 1/4 and 21/8. Okay, so there's my inflection point, I believe. I mean, we have to determine whether this changes concavity or not. So how do we change concavity? Well, just like you do with increase and decrease, you set up a sign chart. So here I'm going to set up a sign chart again. I say again because I did another video on this exact question, just looking at increasing and decreasing. The difference in this one, though, is I'm looking at the second derivative because I want to find concavity. And the only point of interest here is negative 1/4. Alright, and then I'm going to pick some test points, so something below negative 1/4, how about negative 10? And something greater than that, how about just 0? And all I need to do is plug these into the second derivative. So I need to plug them into this expression. And so generally we set it up something like this. You have 24x plus 6, and I have my test points negative 10 and 0, and all I care about is whether the second derivative here is positive or negative. So if I plug in negative 10, you get negative 240 plus 6, that's negative. So the result there is that anything below negative 1/4 will make the second derivative negative. If I plug in 0, I get positive 6, which is positive. So the implication is that any x value greater than negative 1/4 makes the second derivative positive. From there we can determine here, since this is negative, I'm concave down. And here, past negative 1/4, since my second derivative is positive, I'm concave up. So we could write it like this. Concave down on where? Negative infinity to negative 1/4. Okay. And concave up on negative 1/4 to positive infinity. I hope this makes sense. Understanding increase and decrease, local min and max, concavity has a lot of applications. It's very useful. If you need help, please let me know. I'll be glad to help. And thanks for watching.